Exponential functions. Number 1, determine whether y equals negative 6x is an exponential function. Nope, it's a linear function because it looks like y equals mx plus b. You would know if it was exponential if it had an x in its exponent. Determine whether this is exponential. Yep, because it looks like this. Just like this was a linear function, that's an exponential function. Number 3, determine, is this an exponential function? No, because when it's that 1 to the x power, anytime you raise, so like let's plug in some numbers. If you plug in x is 0, okay, well 1 to the 0 power is 1, you get 1/2. You plug in 1. 1 to the first power, and if you're like, what do you mean 1 to the first power? Okay, well let me erase this and like show you. 1/2 times 1 to the 0. Well, that was 1/2 times 1. Okay. 1/2 times 1 to the 1. Okay, well that's 1/2 times 1. So there's 1/2. Let's plug in 2. 1/2 times 1 squared. Guess what? 1/2 squared is 1. So you get 1/2. So this is actually a linear function. Crazy, right? Does this table represent linear or exponential? Well, looks like it's going up by 6, by 12, by 24. Okay. Or you could say that's times 2, times 2, times 2. I would say, yes, that is an exponential function because of the multiplying by 2 parts. So, yes, it's exponential. Great. So this one's a little different in that x is going up by 3 each time, but that's not really that big a deal. Let's look at the y's. So let's see. This is like subtract 9, subtract 9, subtract 9. So no, this is not exponential. It is linear. And if I haven't explained myself, over here, this was exponential because it didn't have a rate of change, like it went up by 5 each time. It is getting multiplied each time. So the fact that it's getting multiplied each time, that's different than if it just went up by 5 each time. And so over here, this one is not being multiplied by like 3. It is being subtracted by 9, and that's why that one's linear. Okay. Number 6, now we're just evaluating. And if you're like, this plus this is a little confusing, don't worry. They're just saying take this, and plug it in for the x. So it's going to be 3 times 2 to the negative 1 power. Well, that's 3 times 2 over, 3 times 2, 3 times 1/2. It's 3 over 2. Evaluate f of x equals 0.5 to the x power for x equals negative 3. So there's our x. We're going to plug it in right there. 0.5 to the negative 3 power. We did one like this in class, and you guys had mentioned changing this to a fraction felt better. Okay, I could see that. So when I am doing a negative exponent to an entire fraction, which is what we're doing there, it flips the entire fraction. So this is just 8. 2 to the 3rd power is 8. Number 8, evaluate y equals 1/4 times 4 to the x power for 3 to the 1/2 power. Okay, 1/4 times 4 to the 3 over 2 power. We're going to break up the exponent. Let's do 4 to the 1/2 power raised to the 3rd power. Because as you may remember, when you have a power to a power, you multiply the power. So 3 times 1/2 gives you 3 over 2. But now the order of operations is a little bit different. We want to go inside the parentheses and see if we can do that first. And yeah, 1/4, that 1/4 doesn't change. 4 to the 1/2 power is 2 because it's the square root of 4, which is 2, right? And then that's being raised to the 3rd power. So we still have 1/4, and now it's times 8 because 2 to the 3rd is 8. And then this is just 8 over 4, which is 2. which is the graph of f of x equals negative 2 times 7 to the x power. Well, right away, I'm going to eliminate this one. Why? Because this one is what it would look like if it was perhaps 2 times 7 to the x power. And if you're thinking, well, I wouldn't have known that. Yeah, you could do that because we've talked at length that 2 to the x power looks like this. Whoop, like that, right? So this negative right here says, well, things are going to change a lot. So we don't like this one. Bye-bye. I don't like this one. Bye-bye. I like either of these two. And then the next question is, okay, well, how do we know which is which? And here's what I'm going to do. If I'm a little lost, I'm going to plug in some numbers and then match them to the graph. So what am I going to plug in? Well, take a look at your x. Your x, what's the word I'm looking for? The scale. There you go. Notice how they're counting 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So that scale is kind of interesting. And then the y-axis is 20, 40, 60, 80, right? 20, 40, 60, 80. So the reason that I'm focusing on that so much is I can plug in a 1, and it will be somewhere along this line, right? And so I know 7 to the 1 power is 7. Negative 2 times 7 is negative 14. So negative 14, okay. If we zoom in here, 20 is here. There's 20. So that could be negative 14. Okay, I don't know if that helps. Let's zoom in here. There's 20. Okay, that could be negative 14. Let's try 2 now. Okay, so negative 2 times 7 squared. Well, that's negative 2 times 49. That's, let's see, if it was 50, then we'd get 100, but we're going to subtract a group of 2. So it's negative 98. So, okay, here at 2, we get real close to negative 100. At 2 here, oh my goodness. It's not that one, right? So it is this one. And if you're like, well, I don't like the fact that we approached it that way. Okay. I suppose the other reason, if you're looking for an alternative reason as to why we like this one, is 7 as our base means we're going to grow very fast. And if you're like, well, what do you mean? Well, 7 to the first power is 7. 7 to the second power is 49. 7 to the third power, I'm trying to squint over to the board. Is it 343, I think? I mean, it's growing tremendously fast. And this one kind of looks more like what we've been doing with 2 to the x, right? Is that, yeah, it's exponential, but it's not quite that exponential. You know what I'm saying? So anyway, it's that one. Let's move on. Which graph is 6 times 1/3 to the x power? Okay, well, you might think, oh, well, it's got to be, oh no, we have a problem. You might be thinking, all right, well, we talked about this. 2 to the x is going to look like this. You're right, 2 to the x does look like that. And this is exponential growth. This, my friends, is exponential decay. Meaning it's going to start big and then get smaller and smaller. How so? Because 1/3 to the 1 power is, well, 1/3, but 1/3 squared is 1/9. 1/3 cubed is 1/27. You see it's getting very small. Like that's 1/3 of a pizza. This is, I mean, let's be honest, 1/9 is, we have to cut this thing up. Oops, I did it too many times. There we go. It's that, right? And then now for this one, we have to cut that like teeny tiny slice up 3 more times. So it's, I mean, it just gets really, really small really fast. So it's not this one. It's not this one, because those are, while they might resemble growth, I mean, those are decay ones. They're just flipped upside down. which, by the way, the whole flipping upside down thing we saw over here, that negative out front made us do flippy things, right? So as you zoom in here, 6 is our initial value. Something else that we kind of talked about, this guy out front is our initial value. Basically is our y-intercept. So I'm actually going to vote for this one now, but let's plug in some numbers to just double check ourselves, okay? So I think we learned a lesson last time that on the last problem, that when we did 1, okay, so that's about 20. We do 1 here, okay, that's about 20. So let's not do 1, let's do 2. So here's 2, negative 2 to be precise. That looks like negative 50. Negative 2 here looks to be, 90, 100. So let's try that. So we're going to take this, and we're going to do it over here just because I've written all over this thing. Negative 2 power. Well, so what we get is that 6 stays the same. This is now 3 squared. That's 9. That's 54. You know what? I was wrong. I thought I liked this one, but no. I like this one better. So let's see. What about that made me... Oh, I was like, wait, why did I pick that one to the right? Because I said our initial value was 6. And as I zoomed in here, I thought, that's closer to 6. But now that I actually zoom in, that's like closer to 4, perhaps. And this one being 6, since that's 10, yeah, that's closer to 6. So, hey, my initial thinking was in the neighborhood, but that's one reason why you want to follow up and check. Right? Right. Number 11? Yeah, number 11. Which is the graph of this? So, okay. Initial value, decay. And if I didn't explain decay well enough over here, the idea is that when we have y equals a times b to the x, when b is between 0, hang on, I should put a b there. B is between 0 and 1, then it's decay. How that? Decay. And if b is bigger than 1, then we have growth. And one thing to point out that we technically already saw is that b should not be 1. B should not be 1, because if b is 1, then what did we see that happened to it? It was linear, right? Which seems odd, that how could it possibly transform to linear? But hopefully you saw here where I was like, look, it was y equals the initial value. That was it. So, okay, we don't have 1, we have 0.25, which falls at between 0 and 1, right? So again, let's look at our answers. It's decay, so I don't like this one. I don't like that one. I don't like those because this is positive, and if it were negative, then we could talk. Let's see, my initial value is 3/2, which is 1.5. So if this is counting by 4s, that's 4. Yeah, okay, that could be 1.5. That's 4. Yeah, okay, that could be 1.5. If we plug in 1, we get like 7. If we plug in 1 here, we get like 3. Okay, so let's check the 1 then. But if you wanted to be, different, negative 2 would be like 24, and negative 2 would be like 8. So it's really up to you. 3/2 times 1/4 to the negative 1 power is 3/2 times 4, which is 6. So let's see. I like this one because, like we said, that is bigger than 4, right? And there's 4 right there. Over here, this is clearly less than 4. 4's right there, so it wouldn't be that one. So I like this one. Next, which is the graph of that thing? Ah, yay. Now we finally are doing that thing, which I just kind of enjoy. If we had regular old 2 to the x, then we have something that looks like this, right? But if we added a +3, it would look like this, actually move left. 1, 2, 3. So the idea is that our y-intercept right here was 1. So our y-intercept here is going to be the same. I'm trying to make that about the same. And it's basically just going to look shifted over essentially by 3. Okay? So let's check this out. Oh, and then another thing is like the y-intercept is actually very easily to calculate because the y-intercept is when x is 0, right? So if you were to do x is 0 here, you get 4 to the 0 plus 3. That's 4 to the third. That's 64. So which one of these, when x is 0, is y 64? Well, no, yes. So there was, I mean, that wasn't too exciting, right? So I guess perhaps the easiest way to go about this one is find the y-intercept. Is that how it always works? I don't know, but often perhaps it works. Describe the domain and range and asymptote of f. So I'm guessing this is like 12 continued. Here we duh. So the domain of f is, let's see, all real numbers. That is the domain. And we talked about this yesterday in class. Again, if it looks like this, you know, x is going to exist everywhere here. X will will approach negative infinity. X will approach positive infinity. The range will not. The range is going to be y is greater than 0 because this thing is never going to touch this line right here of y equals 0. Okay? And then the asymptote is y equals 0. Okay? An asymptote, you know, like this green line and this yellow line, I mean, they're the same thing because they're both y equals 0. Okay, so the range describes what y can be. It is just above 0 and up forever, which is why y is greater than 0. And the asymptote, the line it approaches, the line it doesn't touch is y equals 0. Man, they threw all of the things at us on this one. We have a negative a value, so this thing is going to be flipped. I don't know why I changed colors to do that. Here, I'll do this now. That's flipped. We've got decay. We've got moved left 1. We've got moved down 3. My goodness. So, first of all, no, because that is not flipped. No, because that was not flipped. And then I guess really the easiest thing to check, as we said earlier, is going to be the y-intercept on this. I mean, especially when we've got a multiple choice thing going on. So let's plug in 0. Now, if you have a thought, if you're like, I know what it should be, here's my thought. I think it's that one. And here's why I think so. Because it's negative, so it should be flipped, right? It's moved to the left. Okay, I could see that. And it's down 3. So our initial value of 1, because it's nothing out there, so it's got to be 1. And then down 3, I think it's going to be roughly that. And if you're like, well, that's not exactly 3. Yeah, you're right. Remember, it got moved. So let's plug in 0 and just see what happens. So let's see, I'll do it right here. Negative 1/2 to the 0 plus 1 power. So that's negative 1/2 to the first power, which is negative 1/2 minus 3. Well, we get negative 3.5. Yeah. That looks like negative 3.5. That's like negative 16-ish. So it's not that one. So gold star for this one. What's the domain? The domain is all real numbers because x will be everything along that. The range is, let's see, y has got to be less than on this one. Y is going to be less than negative 3. Shout out to Allie, who helped me to confidently say that this guy right here, that's our asymptote. Asymptote. That's how it's spelled. That's not how you pronounce it. Asymptote. So our asymptote is y is, well, hang on. So our asymptote is y equals -3. And the range is going to be incredibly similar because it's going to be the numbers that are less than -3. And if you're like, wait, why is it less than? Because it's all of the numbers down through here, right? Okay, so I didn't scratch that out because it's wrong. I scratched it out to show the range. There's that one. Let's move on to 14, which is the graph of this. We have an initial value. We have we've moved it down 5. And then this thing is over, I shouldn't say over, we moved it right 1. Okay. So, I mean, let's go with our initial value idea of 3. Okay, so 3 gets moved down 5. So let's see, that's 3, that's 3, that's 3. They're counting by 3s on this. So if 3 gets moved down 5, that would be -2, right? So, I mean, my goodness. So it's either this one or it's this one, yeah? It's moved to the right 1. And I'd said, hey, you know, one of our best bets is to try the y-intercept. I'm looking at both these y-intercepts. They look so similar that I don't know if I want to try out those y-intercepts. If you couldn't see that, I drew this little green dot here and right here. Those y-intercepts are really similar. But you know what? Check this out. 2 is basically 0. 2 is basically 12 here. Let's plug in 2. So here we go. 3 times 6 to the 2 minus 1 minus 5. Okay, so that's 3 times 6 to the first power, which is just 6, which is 18 minus 5. That's 13. So at 2, holy cow, it was this one. Because like I said, at 2, it's basically, I said like, whoa, wait a second. Oh, 13. I was like, I said 18. 13. Yeah, I could see that being 13. But obviously here, 2 is not at 13, right? And if you're like, are we supposed to know that by just looking at this? I don't think so. I don't think you will be that precise. On other ones, you would have been much more precise because there was a slope involved. And so it was like, just go over 2, up 4, that type of thing. Domain, range, domain, it might not surprise you, but the domain is going to be all real numbers again. The domain for functions, you guys, it's almost always all real numbers. Why would it not be all real numbers? I don't think we're going to get into the functions that have holes in them. Maybe we'll do some piecewise functions, but anyway, in that way, there's giant chunks missing, so you could see why it's not all real numbers. The range is going to be y is greater than -5, right? And if you're like, I don't know, I mean, you could look at the picture, but yeah, it's y is greater than -5, and then the asymptote is going to be y equals -5. Okay. Number 15, compare the graphs, find the value of h, k, or a. Okay, so first of all, there's y equals a times b to the x minus h plus k. All right. So the original one, so we're comparing the graph of g is a vertical translation. So they're giving us a lot of information. So if it feels like this is crazy, here's g. It's kind of hard for me to see because it was blue on blue. There's g, okay. And then this one is f. Okay, the black line is f. And it's just saying, hey, g is a vertical translation. How many units up? Well, it would appear that it is 1, 2, 3 units up. And so k is just 3. So actually that one wasn't that crazy now that we looked at it. Compare these graphs. So again, instead of me writing out this thing, I guess the point of writing this thing was to kind of say, this moves left and right. It's the x direction. This moves up and down. It's the y direction. And then a was our initial value. So I'm going to put IV for right now for initial value. All right, but they're kind of leading us saying, hey, horizontal translation. So basically they want to go from the black line to the blue line. It looks like it just went 1, 2. So this isn't that crazy. It's a horizontal translation. 2 units left. So this would be positive 2. And then H is going to be negative 2. So if that's a little confusing, I could see why you might say that. But the fact that this uses words, it says left, well, that kind of gives us this negative 2. Does that make sense? Hopefully it does. Last couple. 17, determine whether each situation can be represented by linear or an exponential function. A checking account receives $500 each month. Linear, because you're going to have 500, then 1,000, then 1,500, then 2,000. That's it. The number of people infected by a virus triples each week. So in week 1, 3 people have it. In week 2, 9 people have it. In week 3, 27. This is exponential. An unpaid credit card balance accrues 1.75% interest each month. We'll actually talk about this. This is y equals a to the, I guess we'll say 1 plus rate to the x power. And it's got to be 1 plus rate. Now, rate could be bigger or smaller than whatever. So anyway, this is exponential, because it will grow exponentially. And if you're like, but how? Okay, well, so if you had 1,000, let's go with $100, and you don't pay, but you have that much interest, well, the next month you owe $101.75, because 1% of $100 is $1. And then I really don't want to do the math in my head for what if you don't pay that, but it does go up. In fact, here, I'm going to pause the video and do the math. Okay, so the answer is you would have $103.53. And by the way, that would be an amazing credit card. I would run up such a gigantic bill because 1.75% is nothing. Right now, credit card interest rates are like 30, 40%. So that $100 would end up being, like 130, and then it gets crazy. So by the way, I did this on my calculator. And here's what I did. I did y equals the initial value of this fictional $100 times 1 plus the rate. Well, the rate was 1.75%, and this is how you would write that. And then just to the x power. So that was days or times it accrued. Anyway, so that was fun. So all I did was put a 2 there, and I got that. A radio station chooses 2 new game contestants each day. 2 today, 4 tomorrow, 6, and so on. That's linear. The graph represents the value y of a boat after x years. Value y, it's here too. And find the value of the boat after 2 years and then after 8 years. Well, obviously they didn't give it to us. Notice it's not linear, so we can't go, it's just -6. -6. We can't do that because it's not linear, right? Now that could be our estimate, but they want us to really do this. So check this out. We have 30 as our initial value, and then we can actually figure out how much it's going down by doing this. We're going to do 24 over 30 to the x power. I know that seems a little crazy. I'm going to reduce that to go, okay, if we divide both of those by 3, we get 8/10. I guess we could have gone a little bit further. We could have divided by 6, so 4/5 to the x power. And if you're like, well, how do you know that that's right? We could use a calculator to check this. In fact, I'm going to grab the calculator to double check my math and see if that looks right. 30 times 4/5 raised to the 3rd power. I really hope I get 15.36, and I do. So this is our formula, and if you're like, how would I have known that? Well, here's how. We knew that we had an initial value, right? And we knew that it was decaying, going down, right? And so this number, this red number, the thing I'm talking about decaying, needs to be less than 1. And here's what we know about all this information right here is that we know we have a table. We could make a table. So x, when x is 0, y is 30. When x is 1, y is 24. We don't know 2, but we do know 3. And in fact, we want to find out what 2 is, so that's one reason why we don't have 2. All this time up here, let's go back. This was exponential because it was times 2. And one way we could have thought of that is, so this was the first term, and then this was the next term. First term, next term. That's 2. And we could have done it again. 24, 12. This is not the second term, third term, that kind of idea. And 24 over 12 is, again, times 2. So back way down here, let's just plug in 2. So if you use some type of calculator to do this, well, actually, I guess I don't know that you definitely did, but I'd probably recommend it. So we get that after 2 years, it is 19.20. I'm doing 20 because it's money, but it could just be 19.2. And then after 8 years, again, I'm using a calculator. So what I'm doing, I guess I could show you if you didn't opt for a calculator on this one, is 30 times 4/5 squared. Well, that's 30 times 16/25. And let's see, if you divide that by 5, you get 5, and you get 6 there. 16 times 6 is 36. Carry the 3, that's 96. 96 fifths. 96 divided by 5. That's 19.2. So anyway, just kind of showing you it can be done by hand. Now this next one I'm not looking forward to because it's 30 times 4/5 to the 8th power. 4 to the 8th power is 65,536. Cool. And 5 to the 8th power is 390,625. Cool. And if we divide those and put them into a fraction, you just don't get a fraction. You get 0.167772216, and if I multiply that by 30, I get 5.033. So this thing is not worth a bunch of money after 8 years. Okay? 5.03 bucks. Not much. Last one. Does the table represent linear or exponential? Seems like we've done this. Oh, or neither. Okay. So let's see. We're going up by 1, and this goes up times 5. So they didn't do times 2. They didn't do 2. So let's check this out. What if we reconstruct this table? So the second one, if it's times 5, then we would have 50 here. I don't think we do because notice 3 is 50, right? And 6, well, so we missed 4 and we missed 5, and then there's 6. It's 250. So this is not linear. I'm sorry, this is not exponential. And let's see, if it were going to be linear, okay, well, that was plus 8. So this would be plus 8, which would be 18. And plus another 8 would be 26. So this is neither. I don't know why I just scratched that out. It's neither. So there we go. That was the whole exponential function. Emphasis on the function. Let me know what questions you got. See ya.